This is the fifth video in my series covering materials for A-level, pre-university or high school physics. In this video we're going to look in depth at the Young's modulus, which is perhaps the most important part of this topic. Young's modulus is given the symbol E and is defined as being stress divided by strain. What we're thinking about here then is actually the gradient of a stress-strain graph. Stress, we know, is force over area. So if we divide that by strain, which is extension over original length, we get one of these rather ugly looking 4-level fractions. Nobody wants to work with these. And the way to deal with this double-decker fraction, if you like, or this quadruple lever fraction, is to remember that you can flip the bottom pair over and then multiply it by the tops. In other words, this simplifies, and it is a lot simpler, down to E equals F over A times L over extension. Now, if you don't like the maths, this is something to commit to your brain of memory, because you will use this over and over again. So, what units does Young's modulus have? Well, if it's stress over strain, then it's just newtons per meter squared over, well, nothing, because strain doesn't have any units. Therefore, Young's modulus is also measured in newtons per meter squared. And as a general rule, the kind of materials you're going to use in your exam, this is always a big number, generally over 10 to the 10 newtons per meter squared. One of the useful things about Young's modulus E is that its value is always the same for a material, provided you don't change its temperature. It's therefore a bulk property of that material. And this means that if you're an engineer, say, and you need a piece of steel or something in a particular place in the building and you know what the length is, you can work out, provided you know what forces you want the material to withstand, how wide, or what your cross-sectional area, perhaps I should say, is going to be for that material. Let's try an example to see how this plays out in real life. Imagine a crazy situation where you want to hang a small car from a steel cord or a steel wire. And the car has a mass 1300 kilograms and the length of the steel wire is to be 3 meters. And it mustn't extend to more than 3.1 meters when it's fully loaded. You're given the value of Young's modulus, 2 times 10 to the 11, and asked to find the cross-sectional area A. Given that we want A, then I would firstly start by rearranging the formula. It's always best to do your algebra last, isn't it, with this sort of stuff. So there we go, FL over E delta L. Now put in the numbers, the force 1300 times 9.81, turn it into newtons rather than kilograms, and that's going to be hung on an original length of 3 meters, divided by the Young's modulus, 2 times 10 to the 11, multiplied by the extension, which mustn't exceed more than 0.1. And when you calculate that, you get 1.9 times 10 to the minus 6 meters squared. And if you wanted, you could work out how many millimeters that is, and you might be surprised that it's not very many. Many materials, at least the ones that you're going to get tested on, should they come up in the exam, will follow a stress-strain graph like this. Now, all that really has happened here is that kind of an extra section has been added on the end there. So let's talk about what's going on. So we have our traditional and much understood limit of proportionality there, and you can just see that there's a slight curve coming now as we move up to the elastic limit. And we know about the elastic limit, as we've said many times already. That's the point to which, if you start taking the load off, it will go back to its original length with no strain. Remember, strain is just a measure of how much the material has grown. But what's this new point here? Well, this is known as the yield point. And it's a point that most of us have had some sort of practical experience with, especially those that are perhaps, shall we say, slightly older. Now, in the old days, before you lot remember, we used to go shopping in places called supermarkets. And in supermarkets, you would be given plastic bags. And what happens is you'd fill the plastic bags up with your baked bean tins or your soup tins or whatever it was, and the bag would grow. So you'd be moving up the stress-strain curve for the plastic, and you'd very quickly get beyond the elastic limit. But if you kept loading the bag which many of us did, you'd get to the yield point. Now what the yield point is that it just goes bananas and just grows and grows, even if you take some of the force out of the bag. And this is the point at which the bag just goes and dies, and all your tins fall on the floor, or the handle breaks or something like that. Now, many materials will actually behave like that, including some metals. So it's not just a plastic thing at all. So the yield point is when it just, even if you take the force off of it, it just continues to grow. You don't have to put any more load on, it's just gone.